Well, I think we can start. Welcome back, everyone. So we're just about done with the semester. We've got about a week and a half, then the final exam, and that's pretty much it. Our goal is to get through section 12.2, which we're currently on right now. And then if we have time enough to get through section 12.3, that'll be our final section of the entire semester. So congratulations again. I think statistics is a tough class to get through, and we're just about at the end. Any questions about all, folks, before we go through the announcements of the day? Okay, one thing I did definitely want to announce, but I forgot, was this extra credit opportunity down here. With all the craziness with the projector and canceling class, I think it just kind of fell off my radar. But the way this goes is everyone has the opportunity to evaluate your class and you're at ISU, not just this class, but every single one of them. And it's also a requirement by the State Board of Education. I mean, they can't force you to do the course evaluation, but they'd be very happy if you did. And I'm offering an extra credit opportunity. May not be the best in the world, especially if you're doing really, really well on your quizzes, but here's what I'll do. If you do the course evaluation and take a screenshot or a cell phone picture of the completion page and just email it to me, then I will drop one additional quiz grade. If that doesn't affect your score, since if your quiz grades are really high, and I'm only already dropping 3 as a guarantee, then I'll move over to your web assign and drop an additional web assign assignment. I feel like that's just the next best thing. If you complete this by Friday, then you'll get that credit. And that's Friday, December 8th. So still some time to get through it. It's pretty fast. Folks say it takes about 15 minutes, but that's if you're putting in a lot of detail. It's completely optional how much detail you want to put into the evaluation. The things that you should definitely mention are things that you felt worked out well and things that you felt did not work out well. It could be about the course material, the instructor, web assign would definitely be a good one to talk about. Anything like that is that kind of feedback that they would like to see. And as far as that feedback goes, it's completely anonymized. I don't even see it until the semester is completed. Sometimes I see them in like summer semester. And the way to find them is it's right here. There's a so-called block drawer right here. You click on it, it pops out just more options. I don't use a lot of stuff up here in Moodle, so I never really talked about it. This is the one thing that you would want to pop out the drawer for this class. Click on this thing here, and you'll see a short blurb of why they do course evaluations. We're in a state university, and the state of Idaho partially funds us, so they just want to know if the classes are even doing a good job from the actual students. So if you click here, that's your survey. At the very end, it's a thank you page. Just take a screenshot, email it to me, and you get that extra credit. Any questions at all about that so far, folks? Okay, a number of people have already done this and did it the moment I put it up on Moodle, so that's awesome. And if you've already done it but didn't know it was for extra credit, that's actually okay. Let me show you what I mean. So if you've completed this, you can just click on it again. It'll say you've already completed the course evaluation for this class. Send me a picture of that, and that works just as well. So that's the so-called course evaluation. I can't force people to do it. It really, truly is optional. So it's all up to you if you want to do that or not. And it will be for extra credit if you do decide to pursue it. Any questions about that at the moment? Okay, so we now have several extra credit opportunities. Maybe we'll go through them again after we complete the announcement page right here. So currently we're in section 12.2. And I did post a couple links from Wikipedia. And if you're curious about statistics, these are a couple of huge figures that you might want to know about, especially if you think you might take more and more statistics or quite a lot of it. One of them is Sir Ronald Aylmer Fisher. This person is considered to be the grandfather of modern statistics. He was thought to be a genius by a lot of people who worked with him. But to me, the biggest role model in statistics and in the data sciences is really William Seeley Gossett. He is the person who masterminded the t-distribution, which is going to allow us to do a confidence interval for a population mean in the most accurate way possible. And it says here in the quick blurb, Fisher believed that Gossett had effected a logical revolution, and it really was true. It took a man like Ronald Fisher to recognize the impact of the work that Gossett put out, and he published it again as an anonymous pen name. So that was pretty remarkable, and that means as a student, we have lots of statistics to do because of all that work that was done there. We do have a weird issue with some of our calculators in class. The TI-84 that I use is a pretty powerful calculator, and it can give us the critical number T star right here for the confidence interval. But that won't work for the TI-83 calculator. That's kind of unfortunate. There's just one function the TI-83 calculator does not support. And the only reason I didn't ban the TI-83 calculator outright was I felt like if you saved money and bought that calculator, it was still worth it. And here's how we'll compromise. We still have to get T star if we're doing a homework problem or a quiz problem. But if we're doing this on a final exam, you are allowed to use your TI-83, and I'm just going to print on the exam itself the T star value that you would have needed. It's not a huge part of the exam, and you'll have seen it already in homework as well. But as far as the homework goes, if you're using a TI-83, you'll really have to use this calculator right here to get your critical value out. Sometimes folks using the TI-84 use this calculator as well, just kind of fast in comparison. And I'll show both methods when we go to do our confidence intervals. So that's our announcements pretty much on this first page here. We continue to scroll down. We have our last quiz, quiz number 13. So this is the final one for the semester. It'll be based off doing a confidence interval like we'll see in 12.2. So the 2 filled out examples at the end of the notes there will be really great models for helping out with the last quiz here. Then after that, here's the other extra credit opportunities we've been mentioning. The final exam can be a form of extra credit, since if you had a rough exam, say maybe exam 2 or exam 1, even possibly exam 3, although I think as a class that was one of the better exams, then you should never really be punished for one exam, dropping your class grade by a letter grade or more. If exam 2 was, say, a rough one for you, then if your final exam score is higher than your exam 2 score, it will replace it. I won't replace a score that will cause your grade to go down, so this will only happen if it helps your grade. Any questions about that opportunity there? Okay, we keep on scrolling down, then here's where we'll have our final exam. This is finals week. It'll be on Monday, December 11th, and oh dear, I thought I put the information in here. I'll fill this out. It's going to be from 8 to 10 p.m., kind of a rough time, but let me put in a notice here. I need to definitely get that into Moodle. Oh, does it? Oh, thank you for spotting that. Yeah, I was looking up here and I just completely forgot. Thanks for seeing this right here. So it's from 8 to 10 p.m. I did mention if that's a bad time, I'm giving an earlier one from, I forgot that time, 3 to 5. That sounds about right. Thanks for mentioning that. So if that's a better time for you, just send me an email at any time and I'll have an exam ready for you if you'd like to take it earlier. For some reason, they think if it's a night class, this is a time people would like to take their final exam. I'll definitely be here because I am giving another exam at that same time in this same class. So either way, you can come up early or later on, and I'll be just happy to help out. But be sure if you're coming earlier, send me an email so I can be prepared, and also so I can mentally prepare to give you the right exam and not the wrong one. I've actually done that before. Well, there's also review materials down here. If you click on this one, this is all the sample exam problems you've seen to date, and it goes to the more current stuff. Let's see here, we're into chapter 10 all the way through 12.3. 12.3 is the one that's kind of questionable. And so if we don't quite get to that, then I'll mention this one won't be on the final exam. Then if you open up this one, this is just the blank lecture notes, all of them that we've been working on. So you can think of them as worksheets. I probably wouldn't print this one out, but if you decide maybe I need to focus on chapter 5, that might be a good one to go back to, work those problems again. And you can scroll up to the notes up here. It's quite a ways up, there it is. All these would be the solutions to those documents that you could take a look at again. And then the last new thing is all the quizzes are posted here as one major document. Every one of those quizzes that we've done, including the one that is right here, quiz 13, is posted on this. And the way I wrote those quizzes they're essentially from old final exams. I felt like these were questions that were really great questions that targeted the actual core objectives of the course. So these are real final exam style questions. If you go through them again, it'd be another great way to practice the course. Well, that's my spiel so far, folks, to start us out. Any questions or comments at all before we get started? Yeah.
I feel like in some of my final exams, it's comprehensive, but there's more like an emphasis on the stuff that we hadn't been tested on yet. Is that how this one is, or is it like pretty like equal through all sections?
I'm going equal through all sections. Yeah, the major reason for that is I feel like trying to get a lot of emphasis on these most recent sections, particularly chapter 12, that would be really rough because I need time to have folks try out homework, do quizzes, return your quiz with feedback so you can internalize it. So pretty much as far as chapter 12 goes, I'm pretty much just going to go for one question. As far as chapter 10 goes, I'm either going to ask one from chapter 10 or one from chapter 9. So I'm not going to try to double up a whole lot of questions from that content there. I would say think of it as comprehensive with a pretty even distribution throughout the course. Yeah, go ahead.
So would most units just have one question based on it?
Yeah, pretty much. And there's going to be plenty of units that I have to skip outright, since if I asked a question based off every single concept we've seen, that's more like a 6-hour, maybe a 4-hour exam altogether. So kind of my goal is I go through all of these documents here, and I have to take a representative selection of these, kind of like selecting a random sample or something like that. That just is a good representation of the core concepts. So probably I would go, not necessarily a question from each one of these sections, but more a question from each chapter would be more along the right lines. Other questions about that so far? Okay, thanks for those questions about the final. I think those are the right kind of questions to ask so far. Any other questions, folks, before we get started? Okay, more questions come up about the upcoming final exam. Don't hesitate to ask. And I lost my place again. There's where the information is down below. Oh, I also should remind ourselves that we did make a change on the notes. So just like before, it's a good idea to get started on this early. And what I would do is go back to your exam 1, exam 2, exam 3. If you still have the notes that you wrote out for those exams, it'd be a good time now to put those together and write out 2 pages worth of notes, and you'll be able to see what stuff did I actually use from exam 1 notes, exam 2 notes, and so on. If you know that there's something you really had to use, maybe something like the empirical rule, the 689599.7 rule, or a Z-star table, definitely include it on the 2-page of notes here. So it'll be the same kind of deal here. It'll be front and back, anything you like on it. Only difference is 2 pages are allowed this time. Aside from that, also there'll be a requirement of a TI-84 calculator. I'll have loads of spares if anything goes wrong like before. But this is still part of the exam, which is something we have to be prepared for. Knowing how to use a calculator is also considered part of the exam. So when you go to study, it might be a good idea to go back and think, what were the big calculator problems? It was stuff like importing data, getting summary statistics, regression type problems, and then finally doing things along the lines of normal distributions. So those are the major things that you definitely would want to brush up on before the exam. And it doesn't hurt. I've seen some people do this with great success. You can put on your notes just quick little reminders of how to achieve something in the calculator. Maybe, for example, you could put in the notes, how do I do a regression if it's asked for? I would follow these steps in the calculator. That's a good thing to include there. Well, I've talked for a while now. Any questions, folks, before we jump back in? Okay, so we are finally now in this section here. Oh, not 12.1. I opened the wrong document. We're now finally in 12.2. So we're going to be dealing with a brand new central limit theorem that we took a preview for in section 12.1. But part of our goal now in these notes is to notice the problems that we were encountering in the last section. So just like before, the first rule of the central limit theorem is when we look at the sampling distribution of X bar, the central value, the average, is the true thing that we're looking for. Mu, the average of the entire population. Standard deviation is given as sigma divided by the square root of the sample size. And then these rules are just relative to whether or not we can use the normal distribution. So for example 1, we're going to look at the major problem with this. It says here, the central limit theorem allows us to calculate confidence intervals. It'll also help us with hypothesis testing. And one confidence interval that was used in the past had this format right here. It was X bar plus or minus Z star times sigma over root n. Here, the Z star, it's the same critical value we've been using in chapter 9 for the different confidence intervals. captures the central C% of area under the normal distribution. But we really can't use this confidence interval in the normal way. Anyone recall what the major problem was? Exactly. This sigma right here is just as unknown as the value mu is that this confidence interval is trying to estimate. So we can say here, just like you said, sigma is unknown. This is a massive problem that they encountered in the past, and this is how they got around that problem. We in fact did it ourselves, but we still had an extra issue. We needed a standard error. The way we get the standard error is we use the fact that sigma is approximately equal to S, which is the standard deviation of the sample of n individuals or objects or so on. So if we could approximate sigma, then there'll be an approximation right here. So consequently, we can say this means the thing that we couldn't calculate, this whole portion, sigma over the root of n, is now well approximated by S divided by the square root of n. And this thing is equal to, let's actually make a new line for this. Let's say this means our brand new formula, SE, stands for standard error. The parentheses are just a way to say of. So it's the standard error of X bar goes in the middle, and it will be the statistic S over the square root of n. So this is our major solution. And for quite a while, this was pretty effective. People got great conclusions that did pan out. They really did work out. But some people were working with smaller sample sizes, and this is where William Seeley Gossett came into the picture. He noticed with sample sizes that are small, around 3, 4, 5, and 6, if you use Z star, you're using the wrong thing. And it's very, very apparent at low sample sizes that that's not the right object. The reason this is suddenly wrong is if you make an estimate right here, well, the confidence interval itself is an estimate of mu, and now we have estimates on estimates. Our confidence interval must be wider to encapsulate this extra uncertainty. So that's the problem with Z star right here. Let's add that just to the notes to explain why we're doing all these different types of computations all of a sudden. So this value of Z star, since we estimate sigma over root n with SE of X bar, the standard error, let's just write it in for emphasis, S over root n, we have even more uncertainty in this confidence interval. All right, CI for confidence interval. And so there should be a larger number here. So this takes us on an adventure of discovering what is that larger number. And this is the work that William Seeley Gossett did. He came to a new distribution called the T distribution, and that's what we're about to take a look at next. First, any questions, folks, before we take a gander at the so-called T distribution? Okay, so here's how it goes. On the notes, I have something called important properties of the T distribution, and then loads and loads of white space. The way I was trying to work this portion of the notes is by going back to the Moodle website, and let's take a look at this document right here, normal and T distributions. The best way to look at a brand new distribution is compared to something similar, and the normal distribution is definitely highly similar. So here's how it goes. It's pretty much a PDF, or no, it's a PowerPoint converted into a PDF, so it looks kind of funny. Here, we're going to investigate how the T n-1 distributions compare to the n01 distribution. So the n01 let me put a correction on the notes here. This is referring to normal with mean, mu equals 0, and standard deviation sigma equals 1. That was used in a different textbook, unfortunately. I forgot to update the notes right here for that first page. So that's what we're taking a look at. And if we go to the very next slide on this thing, here's what it looks like. So N01, that's just the normal distribution, mean 0, standard deviation 1, and that's the yellow curve. Let me put the notes here for that correction. So this is normal, mu equals 0, sigma equals 1. Again, apologies for the, I guess I could call it a typo. I forgot that the old textbook we used this right here, but our author uses this more, I think, less convoluted notation right here. She just says what it is. Now we're going to compare it to the Tn-1 distribution, and that's this one right here. So this is the Tn-1 distribution, or the student T distribution with degrees of freedom, sample size n minus 1, so 1 degree of freedom. So this is what it looks like, and if we add this to our document, we can make some interesting observations right away with this thing. Okay, so here's that. Just trying to make this a little bit smaller. There we go. Here's our distributions. And it says here, the T distribution corresponding to any degrees of freedom, that's always the sample size here minus 1, is bell-shaped. So the T distribution is the one that's going to be in blue. And yeah, it is bell-shaped, nice bell-shaped or mountain shape. Centered at 0, that's what we see down here. And that's just like the normal distribution. But every T distribution has greater variability. There should be more variability because of this problem right here. We made an estimate, sigma approximately equal to S, and so we need to be punished for that estimate by admitting there is more uncertainty in the problem. More uncertainty means more variability. And here's how it's going to work. Let's suppose on this problem, we're doing a confidence interval at C equals 0.95. If we're using the normal distribution, the one in orange, then the picture would look something like this. This captures the central area under the orange curve, and you get a z-star pretty close to 2, about 1.96. But if we're trying to capture the area under the right curve, which is Tn-1, 95% goes way further out. It looks like this. If I want 95% of the area now under the blue curve, you'd probably be somewhere right around here. This isn't perfect. This is just a visual estimate. Probably somewhere right around here. And this area is now capturing the central 95% under the correct distribution. This would be your T-star value. It's always bigger, and it should be. We have extra uncertainty when we estimated sigma using the sample standard deviation, and this is what it looks like. Our confidence interval is going to be wider because T-star is now bigger to encapsulate that extra uncertainty in the extra estimate. So that's what happens when you do a study with sample size 2. Now that's kind of rare, but William Seeley Gossett was encountering these kinds of studies. If we increase the sample size, a mathematical miracle will occur here. And this is why the T distribution was really hard to find. So if I hit right here, the thing that's changing is sample size is 3. That's pretty quick, but let's see what happens. Now let's recall, yellow is the normal distribution, blue is the new thing. Increase the sample size, the blue curve went up a lot. Now there's less uncertainty. And that means, well, if you have sample size 3, and you made the estimate right here, S is approximately equal to sigma, that estimate is actually quite a bit better. You have more data. And that means there is less uncertainty here, and the critical number T-star isn't as big. So we start to see less variability. Bump the sample size again. Now we're up to 6, so I doubled it. The blue curve, which is the new student t distribution, is starting to look an awful lot like the standard normal distribution. Increase the sample sizes and it becomes more apparent. This is why William Gossett's work was so hard to detect, because a lot of studies were around this range. There's not too much difference between the two curves. Around sample size 30, it's really hard to tell them apart completely. Well, if we take a screenshot right here, then we can say with the next couple facts, as the number of degrees of freedom increases, which is infected by the sample size, the variability decreases. But if it keeps on increasing without bound, the larger and larger your sample size, the closer and closer we get to this picture right here. The t distribution is essentially the normal distribution around sample size 30. That was also the cutoff of the rule of thumb, where the essential limit theorem begins working really, really well. But even at a sample size 30 or a sample size 1,000, we still don't use the normal distribution. It's hard to see here, but t star is still bigger than z star. We're still making an estimate, sure, with more data, but we're still capturing the right amount of uncertainty in that estimate by using this distribution. This is all pure probability theory, really. And now when we use it for the confidence interval, it's applied probability. It becomes statistics. So this is a huge amount of mathematics. If you're curious about it, then more and more statistics, you start to encounter the derivations behind all the machinery that's going on behind here. But any questions so far, folks, with those pictures of the t distribution? Okay, it's really hard to calculate these kinds of things unless you use a calculator like this one, or if you don't have a TID3, you'll be using the inverse t calculator right here. This is what it looks like, and you always use the two-sided t-score. I'll demonstrate that when we go to do our confidence interval examples. Well, let's take a look at then the full procedure. Really, all we needed was information about t star, and now the one sample t confidence interval for the population mean mu can finally be specified. So we need two conditions to be met. We must have either random data or assurances that the data came in a way that's representative of the underlying population. Like before, you probably know what I'm about to say here. With part one, in a real problem, a quiz or an exam, we'll briefly discuss this. We'll just say whatever they tell us in the problem, but we won't take too much time. So I'll put here, briefly, discuss. And now, one thing to observe here is the conditions are a little bit easier than when we were dealing with categorical data. Condition 2 is just the rule of thumb that the author is using. The sample size is large enough, greater than or equal to 30. The population is approximately normally distributed. That does come with caveats that we mentioned before, but I'll write here, carefully check. Meaning all you'd really say is the sample size of the study is this amount, which is either greater or equal to 30 or not, and just give a conclusion. Either the sample size is large enough or it's not large enough. So next, our confidence interval procedure looks like this. We take a sample mean, that's the point estimate of mu, add or subtract our new critical number t star, multiplied by the standard error. And the standard error is not too bad of a formula either. It almost seems kind of weird that we're doing this procedure in chapter 12 and not chapter 10. The reason for that is, although it looks a little bit easier on paper, this thing right here is the only reason our author put chapter 12 where it is, because t star is just a little bit tricky to calculate. T star is the critical number, which is based off, let me do that in a slightly nicer way, df, which equals to n-1 degrees of freedom, degrees of freedom are just how we're telling apart between the different t distributions. And the formula is, we just take the sample size, subtract 1. Now here's the downfall of the t star. And again, the reason why it's in chapter 12, and the reason we didn't do it first, every single new scenario, every single new problem requires a fresh computation of T star. That's a bit unfortunate, but honestly, it's not too bad to calculate, but we'll practice doing it here before we go and look at the larger problems. Any questions, folks, before we do our first T star computations? Okay, just for a refresher, so you see what we're about to do, let's go take a look, again, going down memory lane, at section 9.3. 9.3 was kind of a nice situation. Z star is actually the real thing to use here. And the reason Z star works right here is because we only estimated one thing, P. Here, we estimated here as well. There was only one population characteristic, but for numerical data, there's mu and sigma, two population characteristics, force us into the realm of T star, the T distribution. But here, Z star always works for any sample size for a certain level of confidence. I would still include this on the notes for a final exam. But we mentioned if I ever asked something weird like 96% confidence, I wouldn't ask that for Z star. But if you had to do it, this is what it would look like. You put 96% in the middle as a decimal. We take 1 minus that value, cut it in half to find the area in the left tail. Then we just used inverse norm. So that's a refresher of what we did before. We're about to do essentially the same thing, except it's not the normal distribution, so we can't use inverse norm. And we don't have a sigma value. What we'll have is degrees of freedom. Essentially, everything else is the same right here. Any questions, folks, before we give it a try? Okay, so here's our first run at this. It says calculate the critical number T star in each of the following scenarios. We'll round them to 4 decimal places, which is a pretty common thing to round to for this. So it says in example 1, calculate the critical number T star, or excuse me, the sample size is 10 and the confidence level is 90%. First thing I would do is just transfer that information into the notation we're familiar with. If it says sample size is 10, let's write n is 10. If confidence level is at 90%, we should say C is 0.9 or 0.90. And just like before, it's sometimes really helpful to just put out a graph. I'm not going to require that when you go to calculate a T star in a quiz problem. But let's do it here for the notes just to organize the information. It's a T distribution, so it's heavier tail. I'll draw about like that. That's really weird. Let me see if I can make it slightly nicer. But it's really, in essence, going to look just like a normal distribution when you try to plot these. Really, the only way to tell them apart is plotting them side by side. Next thing we'll need is, let's go to this color. We need to calculate DF. DF stands for the degrees of freedom in the problem. And the formula is not bad. It's just sample size n minus 1. So here it's going to be 10 minus 1. And so now we're doing a T distribution with 9 degrees of freedom. Next thing to put down is 0 just as a reference point. That's more of just a habit. And then let's pull in the confidence level at 0.90. So on 90% of the area, I'll just put a value here. This is going to be negative T star, and a value here symmetrically across 0. Here's the one we want, positive T star. And we're capturing central area of 0.90. So that's the dot diagram so far. I've mentioned this before. Some TI-84s allow you to use central area. So if you're okay with that and comfortable with that, that's a fine way to calculate. But for most people in the class, this is how your calculator is more likely going to work. It only accepts area on the left tail, so we need to find that area. It's 1 minus 0.90, cut in half, so that's going to be a 0.10, divide by 2. And so we get a 0.05 that's going into this tail right here. So that's the area input. And the function we'll use this time is going to be inverse T. So this is where our paths kind of diverge a little bit. If you have a TI-83, I'll show how to do it in a separate way. First, we'll try it in the TI-84. Let me just rearrange these windows just a bit. Well, any questions at all, folks, with the setup of the diagram? Okay, if we're happy with what we see here, this is all we have to calculate. Hit second vars, as is our habit. Go down to skip past inverse norm. This is an easy way to lose the question. We're in a new distribution. We require inverse t. You'll know you're in the right place because if you hit enter on inverse t, it wants two things. The area, here's the area that we shaded at 0.05. It also wants the degrees of freedom. Avoid the sample size. It's always one less than the sample size. So our degrees of freedom is 9, and that does make a difference. That's enough to lose the problem on WebAssign if we don't get the degrees of freedom right. WebAssign is accurate enough to tell, and they're also a bit of a jerk about that kind of stuff. So hit enter on this, and here's what we'll get. Notice on the calculator, let me clear this out because it's almost kind of humorous. Go second vars, inverse t. When you hit enter right here, check the corner of your calculator. Some calculators take a minute to actually calculate that. This is a super hard computation, and they did it by hand in the past. Years of their life would have gone into calculating some of these values for every sample size and every different level of confidence. Brand new, humongous computation. Even the TI-84 is struggling on this thing. Admittedly, this is old technology, so your other newer calculators do it pretty fast. So our t-star is finally, we're going to give it 1.8331, which looks weird, right? We cited the negative value. What it produced was this one right here. Negative 1.8331. But the value we're really going for is 1.8331 here, the positive value. We saw this before when we did it for Z star. It's easiest to give area to the left since that's what calculators accept. That means you get a negative T star, but we typically report just the positive one. You have to ask yourself though, does it really matter? Look at the formula up here. When you get a T star, you will use the positive version and the negative version in the formula. So it almost is not super relevant which one you use, except WebAssign would be going for the positive version when they ask for it. We did it, folks. It's 1.8331. And before we go too far with this, let's mention what we were saying before. We have a big problem right here. You can't just estimate a parameter without consequences. That estimate is tremendous, which means there is more uncertainty in the problem. To account for that more uncertainty, our confidence interval must be wider. And let's go back to section 9.3. When we were at 90% confidence, it was 1.645 for Z star. But if we're at 90% confidence and we're estimating a second parameter using T star, 1.645 turns into 1.8331. And that means this number here got bigger, and the whole interval is getting wider to account for the fact we never knew sigma. So suddenly, this is the right procedure, and that was the whole correction that William Seeley Gossett found that made statistics finally really work in the 19th century. Before that, things were kind of wishy-washy. If your sample size was around here, things kind of worked out. We didn't know why. But if sample sizes were around here, it was obvious that Z star was wrong, and we need to use a larger value, T star. So that's the story finally of that critical number T star. Before we move on though, let's calculate this a slightly different way. If you don't have a TI-84, or if you find that the online calculator is effective, here's what you can do. Again, just as a reminder, if this was a real exam problem, or rather, if example 2 was a real exam problem, I will give this value right here. You would not see part C. The instructions you see on this are more for as if it were a quiz or a problem in WebAssign. Well, let's try this again. So on the Moodle website, go down to, if you have a TI-84 calculator, this document or this link right here, the inverse T calculator. It's not needed for the TI-84. If you click on that link, you get sent here. There's one big reminder on the notes. be sure to use the two-sided t-score. So all you have to do is, in this calculator, change your degrees of freedom. I'm going to drop that down to 9 to match the problem. Confidence level, I'll just type in 0.90 and calculate. And we're done. The two-sided t is 1.8331. Let's see if we still have that right value. We even rounded the same, so that's really good numerical evidence. We're on the right track. So here's how the inverse t distribution calculator will work. And again, a lot of people say after they've done these kind of problems, they just went ahead and used this calculator even if you had the TI-84. It's just a little bit faster. It'll be completely up to your option how you'd like to work with it, but just another reminder here, always use this value. What any questions, folks, on our first critical number T star? Okay, well, for the sake of fun, let's try it once more. Part B says the sample size is now 190. So we're jumping up to a really large sample size study. And if I were to plot these things side by side, the pixel width on the monitor might not even be enough to tell the two distributions apart any longer when sample size get this large. But still, at 190, T star is bigger than Z star, and we'll find it out very, very shortly. Let's write out N is 190. Confidence level is at 0.99. So here's our new distribution to give a try, or to put in the information. Very first thing you want to put in is DF. And we should do this calculation whether or not we're drawing a picture, because we need it for the calculators. Degrees of freedom is n minus 1. In this problem, it'll be 190 minus 1, or 189 altogether. So that's our degrees of freedom. And again, that's actually important to the minus 1. The value you get at 190 versus 189 could be enough of a difference to lose a problem in WebAssign. We really have to get that right value. Last thing I'll put on the diagram is 0 here. Here's negative T star. Positive T star goes here. That's the value we're actually hunting for. We'll feed the calculator the area in that location. Same trick, go 1 minus 0.99. Let me minimize this. It's just weird to see a turkey gravy ad while we're trying to do math. Gotta hate those ads. So 1 minus 99 divided by 2 gives us a 0.01 divided by 2, which is a 0.005. So that's the area we'll give, and the degrees of freedom will be the last output, or excuse me, input. Okay, so this is the moment of truth. On the calculator, go back to second vars, option 4 for inverse T. And now the area we were giving is 0.005. Degrees of freedom is 189. And before we hit enter on this, let's take a look at what we got before. It's not just interesting, it's, I would say, pretty educative if I can find the right document here. Sorry for all the scrolling around finally. It's kind of interesting to see how these change. So with the Z star, we had a 2.58 at 99% confidence. Our sample size was huge, which means T distribution and normal distribution should be pretty close. But our T star this time comes out as a 2.6020, or 21 if we round. It's just a little bit bigger by about 200ths. But you know what? That 200ths is us being honest. We have to include that in the confidence interval to widen it by the right amount. So even though it seems small in an applied problem, 200ths could mean an awful lot. It just depends on the context. So back to our current problem, we just need to record T star is 2.6021 after rounding to 4 decimal places. We did it, folks. That's the hardest thing about doing this new confidence interval for numerical data. For estimating a population mean, we have to reconstruct a T-star on every single new problem. That's an annoying thing to do, but it's really not too bad to get through. It's just an additional step we get used to. Next problem I have on the page here is a full example, example number 2. But this one's going to be a little bit long. I think we could start it, but then we would have to re-talk about it when we come back on Thursday's class. I think this might be a good stopping point for us today. Does that sound all right to folks so far? Okay, when we come back on Thursday, before the weekend, we'll take a look at example 2. This one is very similar to the quiz, so even if we don't make it to example 3, we'll be in really great shape for the upcoming quiz. Well, have a great night, folks, and I'll see you all on Thursday's class.